section 11.2 with circles, arcs, and chords. So this section starts at the center of the circle with a central angle. A central angle is the vertex of the center of a circle. Whose vertex is the center of the circle? So if you take a center of a circle and extend it out to A and B, you make a central angle. An arc is then an unbroken part of the circumference that is created by a central angle going out to the circle, intersecting the circle at 2 points. Anything in between those, that part of the circumference that's caught by the angle, is an arc. A minor arc, so less than 180 degrees, is equal to the measure of the center angle. We can measure the length, or we can measure the measured in degrees. So the length would be a linear measurement, inches, centimeters, whatever. When we say the measure of an arc, we're talking about the degree unit we can quantify it with. A major arc is again an arc that is part of a circumference, but is the rest of the circumference from the minor. So if the minor is from A to B, the major is from A through D to C. So not A to C, A through D to C. That's how we can kind of distinguish it. And that is 360 degrees, the whole circumference measure, the whole arc measure, minus your minor arc. If an arc is created by diameter, it's a half a circle, and the semicircle's measure in degrees is 180 degrees. So we're going to be using this graph to find the measure of the following arcs. The measure of arc FMC. So in the graph here, FMC, let's kind of trace that out. FMC. That is, let's see, pop 9%. That is country 10%. And R&B 11%. Add it all up, that's 30%. And we want 30% of 360 degrees. So 10% would be 36. We want 3 of those. So 3 36s would be 108 degrees. For the measure of arc AHB, so A through H to B. So A through H all the way to B. So that is 3/4 of the circle. So that is 75%. Finish that of 360 degrees. So 3/4, 1/4 is 90. 3 90s, 270 degrees. Then measure angle EMD. So EMD, E to M, back to D. That is going to be 10%. So that is 10% of 360 of the whole circle. and 10% going to be 36 degrees. Alright? So the center angles, the minor arcs, equal measures, you can use them to readily find the measure of arcs, and you already know how to find the measure of angles. Real quick, arc addition postulate, just like there was a segment addition postulate and an angle addition postulate. We can also add the measures of arcs if they're adjacent, if they have one endpoint in common. So finding the measure is the measure of arc BD. Alright? So the measure of arc BD from point B down to D. So we need the measure of arc BC, we need the measure of arc CD. Alright? So BC is going to be vertical with, angle BFC is going to be vertical with angle AFE. So 97.4 degrees. To find CD, measure arc CD. It's going to be 180. So diameter AC creates arc AEC, that's 180, minus 97.4 and 52. So 180, don't feel like doing mental math right now with decimals. So minus 9.4 minus 52, 30.6 degrees. So let me kind of draw that in here if I can. Read the small, 30.6 degrees. So to find the final measure of arc BD, 97.4 plus 30.6. I can do that. I think 128. I hope. Alright, good deal. Alright, so kind of take a look at these other ones also, okay? Now in a circle, within a circle, or congruent circles, congruent arcs are two arcs that have the same measure. Just like congruent segments and congruent angles, there's also congruent arcs. And then this theorem has a whole bunch of results that can take you all the way from the inside of a circle to outside. So first, congruent angles have congruent chords. Angle A creates chord DE. Sorry, not angle A. The angle on the left that has vertex A creates chord DE. The angle on the right that has vertex A creates chord CB. Those chords are congruent. Those congruent chords also create congruent arcs. And congruent arcs have congruent central angles. So I'll kind of refer to this sometimes as ACCA, kind of arcs, chords, central angles. Kind of they're all congruent to each other if they all create each other. So example 3, find measure angle WS. Look at that. Using that theorem 1122 or ACCA. And the last two theorems kind of converse of each other. In the circle, if radius is perpendicular to a chord, then it automatically bisects the chord. So CD is perpendicular to EF, so it then bisects chord EF. And the converse. If JK, the line segment, is a perpendicular bisector of GH, then line segment JK is the diameter. So example 4, find NP. Take a look at this. My advice to find NP is you're going to need to add another line segment into this circle. So take a moment to think, what other line segment could you add into it? A line segment that you would know the measure of, or the length of. And in the circle, every radius is congruent to every other radius. So Rn is a radius, it would be congruent to any other radius in the circle. So take a look at those examples. Check your work with my completed notes online.